So we are on. Surely. So yesterday we have done up to the. I think we did up to 8th slide, where we have introduced some of the basic concepts here. Now, in this diagram, we have tried to analyze this situation in terms of the changes of the temperature or the pressure with the, as we go in the deep interiors of the earth, and parallel fashion, as we have seen that the force of the gravity acts on mass to produce pressure, that is P, and in the interior of the earth the rate at which the pressure increases, which is known as the geobaric gradient. From the basic connotations of the thermodynamics, we have known that the minimization of the Gibbs free energy, or the Gibbs free energy of a bulk of a rock, it depends upon the surrounding pressure, temperature, as well as the chemical potential of the substances. Now, if we try to find out at any given depth the pressure temperature of that particular situation, we have to know the geothermal gradient to understand the point. If there are certain perturbations of the point, we might tell that some of the disturbances might have been caused by increase of temperature or fall of pressure or some fluid activity which had caused the magma to be generated. And now, as previously defined, the pressure is the force acting over a particular area within the earth, and pressure caused by weight of overlying rock is called load. That is called lithostatic load or confining pressure, and it is denoted through this text by P. Do not compare this pressure with some diametric stress, where directionally the stress might be different in quantity, and the magnitude of pressure increases with depth in the earth in particular in predictable manner. To evaluate this increase, we note that the bodies of the rock more than several kilometers beneath the surface are hot and over long periods of geologic time behave as viscous fluids, and like water, which seeks its own level because it has no intrinsic strength. Hot rocks have low strengths and flow readily, particularly over long periods of geologic time, and this concept is implied with the mantle convection and isostasy. And pressure is known as the force by area, that is mg, by area, and from Newton's law of gravity, that can be mg can be substantiated from density, that is rho v, that is the mass per volume of the rock into the volume, that means the mass per unit area, and as we also may redefine the A in terms of P and mg, and if we try to replace them, then this situation comes into hand. Now we try to analyze this situation, that is, we can see, as we have already seen, that the solidus of the H2 saturated granite is always or has a lower temperature than solidus of a granite which is not saturated with H2O, or solidus. Here is another example from the periodicity. Why does this happen? This happens because of the H2O, whenever present in some rock, it can break the structure of the rock, or that can destabilize the silicate network present in minerals in the rock, and that's how, if we try to increase the temperature, it is much more easier the rock to melt down because of the vapor pressure generated inside the rock. That's what happens. And the next thing that is we will be interested to know, understand it, is the properties of the magma. Now here is an example from a lava lake crater probably, and here you can see the different phases or minerals under microscope. Here you can observe that some larger masses, which are known as the phenocrysts, are immersed in a finer grained matrix of the rock. In the rock, it is a petrographic description or the petrographic observation from the rock, as well as you can also see, or you can also verify this from field. This is a core sample probably, and these are the phenocrystic phases. This one, this one, this one, and this black portion is the matrix of the rock. So in a rock we may observe some polymodal grain distribution. That is, there are different sizes which are abundant. That is, suppose 15% to 20% of the rock, which is composed of grains which are 6 to 8 centimeter in length, and 50% of the rock which is composed of smaller grains which are might be quite a few millimeter in its radius or its size. And mostly how the size of the rock or the minerals in the rock is determined, that is actually depends upon the degree of undercooling, how fast or how slow magma is cooling down or not. So in discussing magmatic temperature, it is important to keep in mind that a rock, being a texture, it is a mixture of the minerals. It does not have a single melting temperature. Instead, it melts over a temperature range that is commonly several hundred degrees, because in a rock, when we try to analyze the rock is composed of multiple minerals, and there are contact regions of different minerals, suppose A, B, C in the rock, and the rock will first melt in positions where the minerals or different minerals are in contact with each other. Why? It happens because the least Gibbs free energy possible is developed in regions where the temperature, when the temperature is increased in the or nearby the contact regions, because of the multiple phases in action. And if you try to analyze this situation like in contact phases and coexisting phases, the number of phases increases, okay, in the small domains or the small systems, if we consider the contact regions at the system in the rock. One line of evidence indicates that a magma rarely exceeds the temperature range, and magma that cools rapidly by coming in contact with a cold rock or by being extruded on the surface crystallizes to a fine-grained aggregate of minerals or is quenched to glass. Suspended is the mineral are almost always larger crystals known as phenocrysts, and it is the phenomena which happens by the time when a rock is getting crystallized. Extrusion temperature of the magma, which might differ from 1100 to 1200 degrees Celsius in case of basalts or volcanoes. In case of granites, the extrusion temperature might range between 800 to 1000 degrees Celsius, and increased pressure causes melting temperature to rise. But whenever the water might be present, the presence of the water might diminish the melting temperature of the rock, or rather the crystallization temperature of minerals from a magma. So whenever we are trying to approach this situation now, we are getting two things into mind. One is during melting and one is during the crystallization process. Many important petrological processes are controlled by the density of the magma. For example, buoyancy largely determines the rise of the magma from a source region, and indeed magma that ascend through the lithosphere may have a limited compositional range that is determined by magma density. The lithosphere may act effectively as a density filter. Crystals may float or sink in a magma, and by so doing they can change the composition of the remaining magma, that is differentiation, which is known. is clearly determined by contrasts in crystalline liquid densities and when the magma chambers are periodically replenished with charges of fresh magmas. And this is very important line that is happening. Crystals may float or sink in a magma, and by so doing they can change the composition of the remaining magma. Differentiation and this process is clearly determined by the crystalline liquid densities. Okay, and what the magma chamber are periodically replenished, that is, you find this diagram. This is the diagram where some of the things do happen in the magma chamber. In the mantle depths or the lower crustal to mantle transition region, where the magmas are generated due to the Rayleigh-Taylor instability, these plumose features develop because of the temperature as well as density contrast, and they try to assemble towards upper sections in earth or to the lower crustal sections. While they are going after the partial melting process, the black ant-like features, those are disseminated, which are the restites of the minerals which are left after the melting process, and the yellow ones creating dikes of the as well as seal-like features. They move upwards towards volcanic craters. Now, but the magma chambers are periodically, the bottom magma chamber which we have seen is always replenished by new surges of the fresh magma until there is a problem in the regional geothermal gradient or the geothermal gradient that is transecting the rocks in that region. This may happen below the mid-oceanic ridge, this might happen near the subduction zone, etc., etc. And mixing of the magma may occur. Magma densities are closely matched, but if densities are different, the magma remains separate. And the magma mixing, which plays an important role in generating certain rock types. That is, suppose a basaltic magma is trying to rise up through the crustal sections. If they assimilate some of the sedimentary rocks which are composed of higher concentration of the silica, the magma might change in composition to andesite or andesite. And this is happening because of some assimilation process. So here, if there is a much of the density contrast, like 1 is 5 and 1 is 10, then there will be no mixing because the liquid structures will not permit the fluids to mix with each other, or rather mingling will be the dominant process, where there are some centimetric scale or centimeter or millimeter scale interpenetrations of two types of magma or substance, but there is no chemical mixing between them, creating homogenization. This also depends not only on the density but also upon the viscosity of the different magma under consideration. The density of the magma can be determined in several ways, and first it can be measured directly by high temperatures, and this is technically difficult. And where it is a section, if you read it, you will find it, that is alpha, if that is the coefficient of thermal expansion of a volume, and T1 is the earlier temperature and T is the final temperature. This equation, it is very common, and if you try to substitute the volumetric term by density term, which is mass by volume, this equation goes in the form or becomes of this form, and then by replacing or by substituting and multiplying the top and bottom by this mathematical operation, we can find that density of the magma will be dependent upon the thermal expansion of the magma also. There are other ways to do this operation or to know the density of magma, and here it is how it is done, and is defined by the change in the volume resulting from a change in the number of moles of the component. And if we try to analyze each mole of the component present in the magma depending upon the volume, and we know the molar volume of the magma, we can easily know the density of the magma by averaging the mole fraction of each component, or the composition is more often conveniently expressed in terms of the mole fractions and as the number of the moles of constituents, and the mole fraction of a component I is denoted by Xi, and this is an equation where you can find how the density of the magma can be derived from the molar fraction. It is easy. The most important controlling factor that is not only controlled magmatic activity but the tectonics of metamorphism terrains and the structure associated with them is viscosity, and this can be Arrhenian, the viscosity can be non-Arrhenian as well as a viscosity determines whether a substance is plastic, viscous, viscoelastic or anything else. The degree of the bonding and the silica as they form smaller scale structures in the melt or not on the fluid, this depends on the fluid activity as well as various factors. There are also factors like the size of the crystals which are inside the magma, which determines the viscosity depending upon the Roscoe-Einstein condensate equation. And like any fluid, and the magma deforms continuously under the action of the shear stress, and this is important. But the deformation may be very slow in a magma. When fluid is at rest, there should be no shear stress, and the fluids react to shear stress by the flowing. And the viscosity is known as shear stress by the rate of shear strain. That is shear stress that is known as, that can be denoted as tau, and the rate of shear strain which has been denoted by gamma dot. And actually the viscosity, it is the amount or the quantity that the magma hinders the flow inside or nearby its structure. So I think it is a long video. It is already 16 minutes. So let me stop here.